Okay, we're going to be looking at increasing and decreasing functions. This is actually stuff that we've done before, and we did this conceptually, but now we're going to be using our understanding of finding derivatives by hand to do all of this work. So these first couple, this first page should come as no new surprise to you. The first says if the first derivative is greater than 0, which means the slope is positive, then the function is increasing. If it's less than 0, the function is decreasing. And then by looking at the second derivative, we know that if the second derivative is greater than 0, our function's concave up. The derivative is increasing. And the opposite is true if the second derivative is less than 0. So from the first and second derivatives, we can tell a lot about a function. All right, so given that, we want to be able to find the local max and min of the following functions. So what we need to do is find out when the derivative is either 0 or undefined. So let's find an equation for the derivative. Using the power rule, we know that the derivative is going to be 3x squared minus 6x minus 24. And we want to see when that equals 0. So let's do a little factoring. And you could use your quadratic formula program or solve this some other way, but factoring's nice and easy, I think, here. So we can then set it up as x minus 4, x plus 2. And so we want to know when is our function 0. So we want to know for what values of x will this be 0, and we know that's going to happen at x equals -2 and at x equals 4. And that tells us that we're probably going to have a max or a min. But in order to find max or a min, we know that for it to be a max, the derivative must go positive to negative, and for it to be a min, the derivative needs to go negative to positive. So what we're going to make is a derivative chart, and these are required on the AP for you to get credit in order to show whether something is a local max or min. And the way it looks, we have x values, and we've got the derivative, and all we're going to be looking at is the sign of the derivative. So what we do is we put -2 and 4 and spaces in between. And so here, these are all the values of x that are between -2 and 4. And here are the values of x that are greater than 4 up until infinity. And here we have -infinity to -2. Okay, so we know that our derivative is 0 here and 0 here. And now let's look at this. If we choose a value between -1, sorry, that should be -2 and 4. Let's just choose like 0. If I were to put 0 in here, I'd get a negative number times a positive number, which would leave this as negative. And if I were to choose a number less than -2, like -3, we get negative times a negative, which would be a positive. And a number bigger than 4, like 5, I'd get a positive times a positive, so positive. So therefore, looking at sort of the change, we go from +0 to negative here, and we go -0 to positive here. So that indicates that this is a max, and here we have a min. So we have a max when x equals -2, and a min at x equals 4. Okay, so no problem there. This is something that we've defined before, but just looking at it again, we're talking about a critical number. A critical number we call C. It's in the domain of the function, and So the key thing is that a critical number occurs either when the derivative is 0 or if the derivative is undefined. So here, derivative 0, derivative 0, derivative 0, derivative 0, and at the other points, it's undefined. It's undefined here because it's a vertical slope temporarily. Its derivative's undefined here because it's a cusp, and it's undefined here because it's a cusp. But even though, so we've got zeros in red, undefined in greens, but all of those are considered critical numbers. And a critical point is just the point at which that critical number occurs. So it's when x is c and the y value is f of c. So find the critical numbers for the following function. Well, we need to find the derivative and see when the derivative either equals 0 or is undefined. So the derivative is 5x to the fourth minus 20x cubed plus 15x squared. And we need to solve this, so let's factor it. We can take out a 5x squared, and what we're left with is x squared minus 4x plus 3. Factor it a little bit more. Notice that at this point, our calculus has become very dominated by algebra, and it will continue to be that way for a little bit longer. So algebra, basic algebraic skills are relied on heavily here. So the critical numbers, c can either equal 0, because that would make that 0, 1, because it makes that 0, or 3. Those are the critical numbers for my function. If I asked for the critical points, I would take each of these x values and put them into the function to get an x and a y value. What about this? Find the critical numbers for this function. Well, we need to find the derivative, and we're going to use the quotient rule. So it's low, d high, and the derivative of e to the x is just e to the x, minus high d low, and the derivative of the low is just 1, all over low squared. So now let's simplify that a little bit. We can pull out an e to the x, and what I'm left with is x minus 2 minus 1, all over x minus 2 squared. So when will g prime of x equals 0 or be undefined? Well, that's going to happen when x either equals 3, because that'll make the numerator 0, which makes my derivative 0, or it will happen at 2, because that'll make my denominator 0, which will make my derivative undefined. So these are the two critical numbers for my function. Notice that there's this e to the x. Well, e to the x can never be 0, so it's essentially ignored. Okay, find the critical numbers for this function. Well, here it's a product rule, or what would be easier instead of using the product rule, and I'm saying product rule because there's two functions. There's this function and there's this function. I think it might be easier to distribute the function so that we don't have to even use the product rule. If we do the distribution, we're going to get 4x to the 3/5 minus, when we multiply this by that, we're going to get x to the 8/5. So my derivative, h prime of x, is going to equal 4 times 3/5 x to the negative 2/5, using the power rule, minus 8/5 x to the 3/5. Okay. Simplifying this a little bit, we get 12 over 5 x to the 2/5 minus 8 times x to the 3/5 over 5. Well, now we need to get a common denominator. So I'm going to need to multiply this by x to the 2/5 over x to the 2/5. And by doing that, now I have a common denominator. And we can add this fraction and simplify it a little bit. So doing that, we get that h prime equals 12 over 5x to the 2/5 minus 8x, and that's what you get when you multiply x to the 3/5 times x to the 2/5 over 5x to the 2/5. Okay, so now we have a common denominator, and we get that this equals 12 minus 8x all over 5x to the 2/5. And we want to know the critical number, so we want to know when that is 0. So it might be worth, just for clarity's sake, factoring the top, and we could factor out a 4, and we get 3 minus 2x. And we want to know when does this equal 0. So when does h prime of x equals 0, or when is it undefined? Well, it's going to equal 0 when the numerator is 0, which happens at 3 halves. And it's going to be undefined when the denominator is 0, and that happens at x equals 0. So these would be my two critical numbers. Okay, so this is something that we've seen a lot, but just defining it exactly. When we talk about local maxes and mins versus extreme max and min, the definition says a local max is that for all x near some value c, sorry, for a local min, f of c is less than or equal to all x in that area. So in other words, like at this point, this is the lowest point in that immediate region. It's smaller than all other values, and that occurs also here. And a local max is saying that for all x near c, f of c is bigger than all those local values. So right there, local max and min. But we've known that before. Here's just a formal definition of what a local max and a local min are, and you should be familiar with that definition. Okay. Important definition, or not definition, but a conceptual understanding. Critical points versus local max and min. Now, critical points, whenever there's a local max or min, if there's ever a local max or min, there will be a critical point. So whenever there's a local max or min, there necessarily is a critical point. But if there's a critical point, that doesn't mean there's a local max or min. So the question is, where is a critical point without a max or min? Where does that occur? So take a second and look. Which one of these points, C1, 2, 3, all the way up to C7, is a critical point without a local max or min? You hopefully guessed it right. This point The derivative is undefined because it's locally vertical, but it's not a local max or min. And this point also, the derivative is 0 at that point, but it's not a local max or min. So those are examples of critical points that aren't local maxes or mins. Okay, so there's to find local max and local min, and we were getting at this earlier. There's what's called the first derivative test, and the first derivative test says that if you take the derivative, and we know this already, if you take the derivative, it's a local minimum if f prime is negative to the left and positive to the right. So when you're proving that something is a local min or local max, especially on a test, especially on the AP test, you'd say this is confirmed via the first derivative test. So that's your rationale, that's your proof. And a local maximum has the derivative is positive to the left and negative to the right. And we've seen this a bunch, but now we're formally calling this the first derivative test. Okay, couple other ideas for us to digest, and then that'll be this for. So we talked about local max and local min. Now we're going to talk about the global max versus local max. The global max is the largest. So for some value c, the global maximum value is f of c, and it's the biggest. F of c is bigger than all x in the domain. So for example, if this is a function, here's a local max that I'm drawing right now, and then the function goes up. So if this is my function, the green dot, here's a local max, but the blue dot, here's my global max. And the global max and the global min, and we've talked about this before, these will either occur at a critical point so it's either going to occur at a critical point or at an end point. And the extreme value theorem discussed before but brought up again says that provided that f is continuous on a closed interval a to b, then f must have a global max and a global min. In other words, there must be some extreme value, the largest value and the smallest value on that interval. So now let's go ahead and look at an example of global max. And here are the steps to finding it. So, if you want to find global max, find all the critical numbers, calculate f of c for each of the critical number, calculate the endpoints, and then just compare. So we want to find the global max and min, so we find the derivative. Well, let's find the endpoints first. So f of 0, I know we're going out of order. I'm doing this step first, step 3. So f of 0 is 0, putting 0 in for f of x, and f of 4 is 12 minus 16, which is negative 4. So those are two possible points. Looking at my derivative, the derivative is 3 minus 2x. So I only have one critical number. So f prime of x equals 0. So we want to know when does this equal 0. And that's going to occur when x equals 1.5. So now I need to evaluate f of 1.5. And that equals 3 times 1.5 minus 1.5 squared. So we need to simplify that a little bit. We know 3 times 1.5, 4.5, minus 1.5 squared is 2.25, and this equals 2.25. So, um, and this is f of 1.5. So if we're looking for the global max and the global min, I only have one critical point, and that's here. And then I've got my endpoints here and there. So to find the global max, I'm just saying, what is the biggest y value? So the global max is the point 1.5, comma 2.25. And the global min, it's the smallest value. So that smallest value is 4, comma -4. And that's finding global max and global min using endpoints and critical points.